by the demonstration of grid connected DC microgrid. So we continue with our talk on day 18, lecture 1. Yes.
Welcome you all for the NPTEL online course on Smart Grid, and today we will be talking about the analysis aspect of Smart Grid. Now, as you have seen almost during last 13 to 14 lectures, where we focused how to develop a smart grid, different components of smart grid and their hardware implementation and analysis. But if you take into a system level, means you have a distribution system having few nodes, few hundred of nodes, and at one node the microgrid may exist, means the microgrid not necessarily to be established at each and every node of the distribution system, but certainly few zones of the distribution system. Now, the question is, when we determine the line currents as well as real power flow, reactive power flow, the voltage at each and every bus, then ideally we have to carry out a load flow analysis, and based on which the potential at each and every node can be determined, that will indirectly tell me the health or the system state. But when you establish smart grid or microgrid at different locations of a distribution system, then the system analysis, especially when you determine the voltage at each and every node, and the algorithm need to be made more robust, and which is slightly complicated compared to the classical load flow analysis. Now, the very standard load flow analysis which has been used in distribution system, let us say it is a forward backward sweep algorithm, where we have the substation or the bus, initial bus, and then we have a load bus, and in between there could be a couple of buses. Now, considering the system is purely radial, and when we see that the load is of x kVA and the source is expected to operate at 1 per unit, for an example. And now what happens, the voltage which is keep on dropping because it is radial, and finally the voltage is altogether different compared to my substation voltage. So, if you start with 1 per unit in a radial system, the last bus may experience a voltage which is close to 0.85 or 0.88. Now, the concern here, how do you determine voltage, because the system is altogether different, and the conventional Gauss-Seidel Newton-Raphson algorithms cannot be extended to distribution system, being the system is of high R by X ratio, and those algorithms cannot be extended, means the transmission system load flow algorithms cannot be so easily extended to distribution level of low voltages, and hence we have to go for a new algorithm, that is forward backward sweep as an example, where we consider that the voltage at the last node is same as my substation voltage. So, knowing the power requirement at that bus, assuming the voltage as 1 per unit, we can determine the current, and further we can determine the voltage by adding the drop, and further we can determine the voltage adding the drop, and so and so. And when you reach back to your from the load point to the substation, we will come to know the voltage is keep on adding 1, 1.1, 1.15, so and so, and finally the substation voltage may be at 1.25 or 1.3, because we had an assumption that the last bus will experience 1 per unit voltage. But because my real voltage is expected to be 1, and because there is a mismatch from 1 to 1.25, the current is not acceptable to me. So, what we do? We assume the voltage once again as 1 per unit at the substation. Based on the previous current, we move further. The voltage is known 1 per unit, the current which has been determined based on the previous step, and then you determine the voltage, and you experience, let us say, 0.98. And you keep on oscillating from the last node to the substation node, and from the substation node to the last node, and hence it is called forward backward sweep. And you keep on doing it, repeat the exercise till the substation voltage is very close to 1 per unit, or the difference between the voltage which has been determined after sweep must be very close to my substation voltage. And then I can claim, oh, that is what the situation is. All the voltages with respect to the last iteration, assuming the substation voltage is 1 per unit, will be my voltage solution of the network. And these are, but now when you have a smart grid in place, then so many new devices, new converters, those have not been modeled in my conventional load flow algorithm. So, the cable modeling, the line modeling, the transformer modeling, the load modeling, the source modeling are common, but the distributed generator modeling, PV modeling, storage modeling, and the converter modeling become the new components that a distribution system can experience in the presence of smart grid. So, now the challenge is, how do you simulate or analyze a system, a distribution system having smart grid along with renewable generations, cables, converters, batteries, etc. And that grid could be a DC smart grid or AC smart grid, or could be a combination of AC DC smart grid. So, let us now move on to the system analysis of distribution system in the presence of smart grid. Now, first of all, we will just cover this portion with different steps like AC-DC distribution network, structure of AC-DC distribution network, classification of buses, overview of load flow analysis, AC-DC load flow analysis and the challenges, power converter modeling, distributed generator modeling, and basic steps for formulating AC-DC load flow. Because when you talk about a DC microgrid along with a AC distribution system, so my system become AC distribution system and a DC microgrid in place. So, then the scenario could be AC-DC distribution system, and we have to now have a load flow algorithm which is suitable for AC-DC system simultaneously. So, what is AC-DC distribution network? Now, in the late 1880s, three exceptionally brilliant inventors, Nikola Tesla, George Westinghouse and Thomas Edison, battled over which electricity system, whether it has to be alternating AC in nature or DC in nature, and which one has to be the standard for future. But due to numerous advantage of AC over DC, finally AC found to be the victorious one, and today we all use AC system in place. Owing to the ever increasing demand, declining conventional energy sources and technology revolution in deploying renewable energy sources, interest is invoked towards DC grid again. Though we have mentioned that the AC system is considered to be the victorious or the meritorious one, but looking into the current scenario of maximum renewable penetration into the system, slowly the DC network or the DC grid taking upper hand over AC. But being said that, we cannot absolutely replace the AC system. It is both, they have to exist together and simultaneously. There are various advantages of DC over AC, but the complete reinforcement of the existing distribution system is next to impossible, and hence DC seems to be impracticable at this stage. So, what we have to consider that the AC system is in place along with DC. A part of the distribution system could be of DC in nature, but the replacement of AC system by DC is next to impossible. So researchers are planning a hybrid distribution network with both AC and DC grids. Now, if you look at the structure of a AC-DC system, it may look like this. So previously, let's say the system is completely AC, where we have the source, and further we have different buses. And let us see, all it is radial in system. It goes this way as well as this way, and you can see few rings in between, loops. And all the buses are AC in nature, which was the initial stage. But now we are considering that there could be few DC microgrids in place. So most of the buses are not necessarily AC, but they could be DC. So all the orange color marked in this diagram belongs to my AC bus, and all the blue color represent my DC bus. So we can see that these are all AC buses, and this is the AC network, and we have DC buses and DC network and DC network. Now please try to understand, when you talk about the loads, those loads are not necessarily to be purely AC or purely DC, and hence loads can be connected, means AC DC loads can be connected at a DC bus as well as at a AC bus. And because of that, conversion from DC to DC, DC to AC, AC to AC and AC to DC is very, very common. Now, what are the major components of a AC-DC network? And the AC-DC distribution system consists of variety of AC-DC components, including loads, generation units, lines and buses. In addition to traditional AC loads and AC generators, it can also include DC loads and DC generators, and perhaps we can include electric vehicles, PV panels, etc. Renewable technologies like PV systems, wind generators also can be considered in our system modeling. Now, power converters, which considered to be one of the very, very important part here, because in our previous distribution load flow analysis, we ideally do not consider the modeling of power converters. But when you talk about smart grid, certainly it has many converters, and without modeling power converters, your AC-DC load flow has no meaning, all right? So how do you classify? Because as you know, in any system, we ideally have actually three different types of buses. One is known as slack bus, and whereas you consider that the voltage and angle at that bus is known to you, and whereas the P and Q requirement at that bus is not known to you. So out of all four parameters, P, Q, V, delta, that is real power, reactive power, voltage at that bus and angle. Now two parameters, those are V and delta, are known to me, whereas P and Q, which are not known to me, is known as a slack bus. Now moving towards a AC, a PQ bus, where the P and Q are known to me like a load, whereas V and delta is not known to me. And in case of a PV bus, where the P is known to me, real power output is known to me, the voltage at that bus is known to me, but the Q and delta is not known to me. So the main challenge for a load flow analysis is how to determine the rest of the two parameters at each and every bus which is not known to me. So at the end of the day, we can determine all the four variables like P, Q, V, delta at each and every bus of the system. So I can say the system analysis of a AC system is clearer. But when you go for your DC buses, now the reactive power is missing, the angle is missing, so perhaps you have only P and V, the real power and voltage, because it's a DC system. Now in DC bus, we have a P bus where we call it as a DC load bus or so-called P bus, where the net DC power injected into the bus is known while the voltage is not known. The P is known, but the V is not known, so called DC load bus or P bus. Now we will have one more bus called as VDC bus, that is DC voltage controlled bus, where the DC bus voltage is known, but the power generated at that bus is not known. First one is P is known, V is not known. The second one where V is known and P is not known. So you can clearly see, now this is my AC bus where we can connect AC distributed generators, we can connect AC loads, we can perhaps connect DC loads, and you can also connect DC distributed generators. Similarly, when you model a DC bus, we can have DC distributed generators, we can have DC load, we can have AC distributed generators, and you can have AC loads. Now very quickly the overview of load flow analysis. For proper planning, analysis and optimal operation of transmission or distribution system, a power flow or load flow analysis become a must. Now load flow study is a steady state analysis whose target is to determine the voltages, currents and real and reactive power flow in the system under a given loading condition. So if the loads are known to me, I must be in a position to determine the voltage at each and every bus, the real power, reactive power flow in each and every line need to be determined. Now the purpose of load flow studies is to plan ahead and account of various hypothetical situations. If the load scenarios are keep on changing, how do I plan my system so that the voltage at each and every node do not violate the permissible variation, maybe 2%, 5% depending upon the utility. Now there are well established algorithms for Newton Raphson load flow, Gauss-Seidel load flow algorithms, fast decouple and Broyden methods. But unfortunately, the distribution system do have high value of R by X ratio and they are weak in nature and mostly they are radial. And because of that, those transmission system based algorithms cannot be simply extended as it is to my distribution system. They need to be updated and modified to suit to my current environment where the R by X ratio could be high, the system could be radial and it is weak in nature. Now the very important AC-DC distribution system is more complex compared to a AC distribution system. It has many elements like new generators, converters whose input and output relations are extremely nonlinear, and hence the modeling or developing algorithm for AC-DC system become a challenge. Now when you move to AC-DC load flow analysis, what are the challenges? Proper modeling of various types of power converters in the load flow equations become important. So how do you incorporate those modeling into your system so to make it more generic? And modeling of various types of distributed generators like PV systems, wind generators, etc. And modeling of storage and various DC loads. The storage need to be modeled and the DC loads also need to be modeled. And finally, taking care of prerequisite control objective by the converters in the load flow equations. The control characteristic of those converters need to be embedded into my load flow. The load flow equations must be capable of modeling the operating state of the combined AC-DC system under the specified conditions of the load generation AC-DC system control strategies. Now there are two different important models that need to be developed. The first one is AC-DC VSC converter model, where you can clearly see that is my point of common coupling. We have VPPC and the PCC, then we have the impedance and then the final output voltage in AC, and then you convert to DC from AC to DC through a VSC, and finally you experience the terminal voltage, which is VDC, and there could be a drop in my DC grid, and finally you experience VDC. So what exactly happened that from the point of common coupling, the voltage is V, and then different stages, it get dropped down, and then because of the line impedances, and finally you convert to DC, and there could be a couple of drops in the DC lines or DC cables, and the terminal voltage could be VDC at kth bus. Now, one more important model, that is DC-DC converter model, where there are few equations where you could see that the DC-DC converter and the bus at 1, and you can experience the bus 2 with a new voltage through a DC-DC converter. And the following mathematical equations are used to model buck boost and buck boost, where equation number 9 and 12 is being used for buck type, 10 and 13 used for the boost type, and 11 and 14 used for your buck boost converters. Now, there is one more important converter known as AC-DC line commutated converter, that is LCC model. The PWM and DC-DC converters can achieve better control objective than LCC at the distribution level. Hence, these converters can be used between the buses as well as between DG and bus for transferring power by fulfilling the control objectives. But if you go for LCC, because they are not so precise, and in that scenario where major control objectives are not highly expected, if you are not looking for major control objectives, then LCC can be used between buses as bus to bus interfacing, but not as a DG bus interfacing. So if you are connecting between bus to bus, please you can place LCC, but if it is between DG to bus, then it has to be it should not be LCC. That's what actually being recommended. Now, the pictorial diagram, a schematic diagram of LCC converter, where you are converting from AC bus to a DC bus, and from bus number 1 to bus number 2, and this is how the LCC being represented or modeled in our analysis. Now, when you model, the next level is distributed generator modeling. We model distributed generators based on 4 types. There are type 1, type 2, type 3, type 4 modeling. And type 1, where this type of distributed generator is capable of delivering only active power, such as photovoltaic fuel cells, which are integrated to the main grid with the help of converters and inverters. So this kind of modeling, we say only reactive real power injection, which is of type 1. Then we will have type 2, where the DG capable of delivering both active as well as reactive power. So it is not simply P, but it is P as well as Q, and we call it is type 2. And further we can move to type 3, DG capable of delivering only reactive power, that is such as synchronous compensators, such as gas turbine are the example of this type of, where they operate at 0 power factor. So you only consider the reactive power injection. And type 4, where you give the real power and take the reactive power out. So DG capable of delivering active power but consuming reactive power, as an example induction generators for the wind farms, etc. So to conclude, all these type of distributed generators can be modeled in any one of these categories as PVDG or VDC-DG or PQ-DG or P-type DG while simulating the load flow equation. So the what in excess we are projecting here compared to the existing literature is that the DG based on type 1, type 2, type 3, type 4 can be modeled, different converters can be modeled, and they can take care of my new components within the DC smart grid, and hence I can simulate both AC distribution system along with DC smart grid simultaneously. Now, what are the basic steps for load flow formulation of AC-DC distribution network? First one, the mathematical model of both AC and DC distribution lines and cables is required. There should be proper mathematical modeling of various types of loads associated with AC and DC distribution system. The most important part is modeling of various types of converters, taking care of control objectives that need to be achieved. Modeling of renewable generators like your PV, wind, could be of PV type, VDC type, PQ type or P type modeling is also required to represent your type 1, type 2, type 3, type 4 DGs. And the suitable unified sequential approach is required to simulate all the mathematical model. And with this, I like to conclude that the distribution system analysis in the presence of DC microgrid become an important issue, and we need to appropriately model those new components, especially the distributed generators of type 1, type 2, type 3, type 4 along with different converters, so that the voltage profile system planning for a AC-DC distribution system along with smart grid presence can be viable. Thank you. A very good morning. Welcome you dear students to the course on Smart Grid, Basics to Advanced Technologies. Today we are going to cover Module 11, Lecture 5 on demonstration of grid connected DC microgrids. Now, as you could see a typical architecture of a DC microgrid, you must have heard about DC microgrids, AC microgrids, even for some extent hybrid microgrids, a combination of both. Now, in case of a DC microgrid, all the loads and generations are connected to a DC grid, am I right? So, if you closely look into the PV panels, those are connected to your DC bus, and even for some extent the DC loads such as electric vehicles or e-mobilities, they are connected to DC bus. And we do have DC-DC converters connected to storage devices which also cater to my DC grid. However, we can also see an AC grid which caters the AC loads. And probably this is a system which is a typical AC-DC microgrid, but will focus mainly on DC microgrid component of an architecture. A typical DC microgrid consists of a DC bus, but you cannot have a system of low voltage network which is purely DC in nature. So, we need to have a DC and AC bus together. So, a typical DC microgrid within a AC-DC microgrid will have both DC bus as well as AC bus. The DC bus is for the interfacing DC sources such as batteries, ultra capacitors, and also cater to some of my DC loads. And in case of AC bus, it perhaps engage all AC sources and also cater your AC loads. Now, the DC microgrid can be able to operate in 3 different modes. The number 1 is grid tied, islanded and autonomous. And perhaps we will try to focus mainly on grid tied as well as islanded mode of operation. And from the above figure, we can see there are 2 switches, switch 1 and switch 2. Those are closed at its initial stage. The DC microgrid is under grid connected mode of operation. What I wanted to tell you, after looking into 2 switches SW1 and SW2, based on its switching on and off positions, the structure or the architecture of this grid may behave differently. From the figure, if both SW1 and SW2, if considered to be closed, then the DC microgrid is under grid connected mode of operation. However, if S1 is closed and S2 is open, that represent DC microgrid is under islanded mode of operation. It serves DC, AC and PCC loads. But in case of SW1 is open and SW2 is open either closed, the DC microgrid is under autonomous mode of operation. So there are three different mode of operation can be experienced through different switching operations from SW1 and SW2. Moreover, the DC microgrid can be controlled in different layers such as zero level control, primary level control, secondary level control and tertiary level of control. In the zero level control layer, mostly grid tied inverter variables are controlled. At this level, the control response should be very fast and in the range of microsecond to milliseconds. In case of primary level control, the control system contains zero level control and is additionally equipped with grid support and automatic load sharing functions. At the secondary level of the control layer, the control system is equipped with microgrid synchronization, voltage and frequency control functions. The control response primary and secondary level control layers are dynamic in nature and slower than the zero level control layer. The tertiary level control layer consisting of optimization algorithms to optimize the power flow, stability and the DC microgrid cost optimization and its operation. Till now, we have seen the operating modes of the DC microgrids. Now, we will try to understand or try to explore the critical features of the DC microgrids. The slide shows the features and various functionalities of the DC microgrid. The significant features of DC microgrid are grid support, flexibility, scalability and stability. Let us look into those features one by one carefully. In the grid support, the DC microgrid is capable of providing ancillary services. In flexibility, the DC microgrid is able to reconfigure the system online during faults by disconnecting from the main grid. The DC microgrid improves the overall system stability by providing sufficient stability margin, steady state and transient operation modes. Further, the DC microgrid increases the system scalability by seamlessly adding more power units. Apart from the features of the DC microgrid, the major functionalities of the DC microgrid are grid voltage and frequency support, coordinated voltage forming and load sharing, harmonics attenuation, energy management between grid and microgrid, serving critical loads during grid outages and so and so. Though we have discussed during the slide, but just for your more attention, I thought that it would be good to repeat again for your better understanding. Furthermore, the DC microgrids are able to work in normal as well as abnormal conditions. This slide shows the block diagram of the L-filtered grid-tied DC microgrid. In this slide, it is shown that the hardware test bed is developed by interconnecting various components. The AC side of the inverter is connected to the AC grid through L-filter. The point PCC shown in the block diagram forms an AC bus where the AC loads are connected. A Hall effect voltage and current sensor are used to measure the voltage at PCC and current through the inductor. The measured voltage and currents are biased to shift the signals above zero level. The offsetted outputs of current and voltage sensors are given analog to digital converter, pins of DSP launchpad TMS 320 F28379D. Inside the DSP controller, the ADC pins read the three-phase currents and voltages along with the DC link voltages. By using Clark's transformation, the ABC components can be converted to alpha beta components. Further, the control logic generates modulation voltages for generating PWM pulses through EPWM pins of the DSP. This slide shows the control logic used for interfacing the DC microgrid with the AC grid. The DC bus voltage controller PI regulates the DC bus voltage at the reference value and generate the AC power reference value. Active current reference is generated from AC power reference as the inner controller requires a current reference. The obtained AC current reference is converted to the stationary reference frame, and this current reference is compared with the measured current, which gives an error to us. The error is further processed through proportional plus resonant controllers, so called PRR controllers, for generating required modulation voltages. The modulation voltages are used for SPWM generation through EPWM pins of the DSP for switching converters switches. They are mainly IGBTs. The control variables of the PI controller and PR controller can be obtained through proper tuning, ensuring that the stability margin should be more. The slide shows the block diagram of the hardware test bed, and in this hardware test bed, the DC microgrid behavior is emulated through a power amplifier by configuring it with Opal RT. In the Opal RT, the DC microgrid is simulated, which contains PV, battery and variable DC load. The scaled down DC bus voltage is given to the analog input of the power amplifier. The current fed to the power amplifier is further given to the analog input of the Opal RT. This creates a PHIL loop between the Opal RT and the power amplifier. The combined operation of the Opal RT and the power amplifier emulates the DC microgrid behavior close to perfection. The behavior of the AC grid is mimicked through Synergia programmable grid emulator, in which semicron 3-phase IGBT based PWM inverter is used as a bidirectional DC-AC converter between the DC bus and the grid. The control logic shown in the previous slide is implemented in the DSP controller. The floating point Texas C2000 DSP controller of TMS320 F28379 Delfino type is used in this hardware test bed. Now, when you move to the demonstration, hardware demonstration of the same configuration, in this module we are very much interested in showing the grid integration of the DC microgrid only. The hardware demonstration of energy management using a DC microgrid will be discussed in the upcoming modules. Let us have a look at the test bed of a grid connected DC microgrid. To avoid complexity in the system and for simple understanding, we emulated a DC microgrid through a power amplifier by configuring it through an Opal RT. How to configure the 4-quadrant power amplifier through Opal RT for emulating as a DC microgrid will be discussed in detail in the upcoming energy management scheme module. In this module, the primary intention is only to show the grid integration of the DC microgrid. For this purpose, we assumed the DC bus voltage of the DC microgrid was quite stable and had surplus power to feed to the AC grid. Let us look closely at the overall hardware test bed we developed in the laboratory for your ready reference. Here the hardware setup shown is used to demonstrate the grid integration of the DC microgrid. This hardware setup is developed by interconnecting various components such as grid emulator, DC bus emulator, DC load, semicron converter stack, filters and AC loads. The DC bus is emulated through a power amplifier and is connected to the DC side of the semicron converter stack. The AC side of the semicron converter stack is connected to the grid emulator through the filter with the help of miniature circuit breaker, so called MCB. Voltage and current sensors are used to measure the voltage and currents of the AC bus and DC bus in the DC microgrid. The measurements are given to the DSP controller for processing and PWM pulses generation to control the converters. Let us discuss the hardware setup in component wise. First, we can concentrate on the grid emulator. This is a multifunctionalities equipment, can be used as a grid emulator, electronic load, battery emulator and PV emulator. This equipment will act as an interface between the distribution system and the equipments under test. During grid integration, the power feeding to the grid emulator is sent it back to the distribution system. During power consumption, it draws power from the distribution system, and this equipment can be configured through a working mode switch to operate it in either AC or DC mode. If the working mode switch is at AC mode, the equipment can be used as an electronic load and grid emulator. Similarly, if the working mode switch is at DC, the equipment can be used as a DC source, battery emulator, PV emulator as well as programmable DC loads. The various functions this equipment is configured with these 4 switches from left to right. The switches are numbered from 1 to 4. Let us see how to configure various functions of this device. Initially, the device working mode switch at 1. This represents the operation mode of the device is DC. By configuring 4 switches, functioning of the device can be modified. After configuring it in a DC mode, the switch combination decide various functions such as DC source emulator, DC programmable load, battery emulator and PV emulator. In this video demonstration, we are very interested in showing how to configure it as an AC grid emulator too. For configuring it as a 3-phase grid emulator, the combinations of switches are: switch 1 at one position represent grid emulator, switch 2 at one position represent the equipment under test is on, switch 3 at 0 position represent the 3-phase that can be independently controlled, and switch 4 at 0 position represent it gives bipolar signals. For configuring it as single phase mode, the only change is switch 3 should be at one position. After configuring it as a grid emulator, the values of the voltage can be entered in 2 ways: by entering the 3-phase voltage values manually in touchscreen. Other way is controlling this device through a GUI or user interface mechanism. The shown window represents software which act as an interface between the grid emulator and user through Ethernet communication. This user interface allows controlling grid emulator voltages in real time without touching the physical device. Desired voltage values need to be entered at 3-phase in the AC operation section of the software. Apart from just entering desired voltage values, it is also possible to monitor grid voltages during experimentation. After entering desired voltages in AC operation, the voltage and current limits need to be specified at the limit section to ensure the safe operation of the system, or indirectly you do not allow this to exceed the operation voltage that you desire it to happen during the experimentation. After entering the desired voltage values and limits, these steps need to be followed to turn on the device output. The first step is to enable the device, which pre-charges the DC link inside the device, After pre-charge, the device is ready to use. Clicking on the run button gives desired voltage at the output point of the device. The grid emulator is connected to an MCB, which is the point where the inverter is connected through an inductor. In this grid integrated DC microgrid hardware test bed, the AC bus voltage is set at 110 volt RMS with 50 hertz frequency. Semicron IGBT stack, we can see here in the video, we have shown a single IGBT stack which has semicron switches and diodes. Before talking about the rating of the IGBT stack, let us look into the circuit diagram of the stack. It mainly consists of two sections. One is the three-phase diode bridge rectifier towards the left, and in the right it is the three-phase 4-wire inverter bridge circuit. The three-phase diode bridge rectifier has the input AC voltage rating of 415 volt and DC output voltage of the rating 560 volts. The inverter bridge has DC input voltage rating of 700 volt and AC output voltage rating of 415 volt RMS along with 30 ampere output current. One important thing to be noticed here is that the DC input capacitor or the DC bus should be rated to more than peak of the grid voltage such that the power can be transferred from the DC side to the AC side. The basic understanding here that until unless you create a voltage difference, it is not possible to transfer reasonable amount of power from one point to the other. For 415 volt RMS AC grid, peak voltage is around 586 volt and the rating of the DC bus is 700 volt. This ensures that there is a sufficient margin for the inverter operation, and in our demonstration we kept higher operating margin by considering the maximum DC bus voltage of 400 volt DC and 110 volt RMS AC grid. The IGBT module used here is SKM75GB12T4. You can see here we have an IGBT module shown in the video, where in terms of the rating it is not same as the one used in the IGBT stack, but physically it look quite similar. Here one module can form an inverter leg, as each module consists of two IGBTs along with the corresponding body diodes. Hence, 4 such modules are used to form a 4-leg inverter. The rating of the IGBT module used in the stack can block voltage up to 1200 volts and also can carry a nominal load current of 75 amperes. It supports switching frequency up to 20 kilohertz. These modules are attached to the aluminum heat sink, which can be seen here to dissipate the heat. These IGBT modules are popularly used in solar inverters, motor drives as well as UPS applications. Within the stack, forced air cooling through fan is also provided for carrying out fast cooling. Also in the inverter section, one can notice that each IGBT module is provided with the snubber capacitors, those are connected in parallel to provide protection against the high dB upon dt. The trigger that IGBT switches gate drivers are required to convey the pulses received from controller to the gate terminal of the IGBT. Each driver can trigger one module, hence 4 numbers of Skyper 32R gate drivers are provided. And these drivers also require isolated DC input of plus or minus 15 volt to operate. Moreover, these drivers have inbuilt dead band protection as well. At the DC link input of the inverter bridge, we have earlier seen two semicron make electrolytic capacitors are connected in series whose ratings are 4700 microfarad, 700 volt each. Across each capacitor, bladder resistors are connected to discharge the stored energy in the capacitors when the inverter is not in operation. Apart from this, the IGBT module also has an inbuilt thermal trip protection feature in case if device exceed the threshold temperature. Let us talk about the detailing of the power amplifier operation. This is a power 4 quadrant amplifier. It is used to emulate AC bus or DC bus voltage by configuring internally or externally. For configuring it externally, the output voltage of the power amplifier is generally controlled by external controllers like RTDS or Opal RT. In this hardware demonstration, we have used Opal RT to control the power amplifier to emulate the DC bus voltage. Here an external voltage signal is used to the analog input of the power amplifier in proportionate to the required DC bus voltage. The rating of the power amplifier is 22 kilovolt ampere and it can be able to emulate AC bus voltage in the range of 0 to 300 volt RMS and DC bus voltage in the range of 0 to 800 volts. For example, the analog input voltage range is 0 to 10 volt, which corresponds to the DC voltage range of 0 to 800 volts. For getting DC 400 volt output from the power amplifier based on the DC bus voltage controller output, the Opal RT gives a proportionate DC signal input to the power amplifier to emulate DC bus voltage. In Opal RT, a PV and battery are connected to the DC bus through DC-DC converters. A DC bus voltage controller is simulated which regulates DC bus voltage based on DC side power generation. In this hardware demonstration, the rated DC bus voltage is considered to be 400 volts. We have used Hall effect based sensors for both voltage and current sensing. A LEM make voltage transducer LV25P is used for voltage sensing while the current transducer LA55P is used for current measurement. Apart from these LEM sensors, the voltage and current measurement sensor circuit also consist of signal conditioning circuits and level shifting circuits. In this hardware test bed, the voltage sensor output voltage to input voltage ratio is 1:100. That is, for the input of 100 volt peak to peak, the sensor output voltage is 1 volt peak to peak. Similarly, the current sensor's output voltage to input current ratio, that is 1:10, means for 10 ampere peak to peak of current, the output voltage of the current sensor is 1 volt peak to peak. Further, the voltage and current sensor circuits are powered by using a DC source of plus or minus 15 volts. Let us look into most important part of this hardware demonstration, which is mainly the DSP controller. We have used a Texas DSP TMS 320F28379D controller to control the inverter between the AC grid and the DC microgrid. The DSP controller is the most economical controller that is used for grid integration applications. For developing any rapid control prototyping, we need to configure the analog to digital converter ADC and PWM pins of the DSP controller. Generally, the DSP controller has 16 ADC pins of 0 to 3.3 volt input range with 12-bit resolution. It has direct 12 PWM pins for generating PWM signals at desired frequencies. Implementing a control system in DSP requires 3-phase voltage and current signals along with DC bus voltage. The 3-phase voltage and currents are measured through sensors. The proportionate output of sensors is a sinusoidal signal, which is a bipolar signal. These bipolar signal cannot be given to the ADC pins of the DSP controller, because the ADC converts only the positive side of the signal into its digital form, and the negative side of the signal is always converted to 0. This causes a significant loss in signal. To avoid such situations, the output of the sensor is given to biasing circuits, which biases input signal above 0 level, and the bias signal is given to the ADC pins of the DSP controller. These ADC pins converts the input analog signal into the 12-bit discrete signal. The control system requires 3 voltage, 3 current and DC voltage signals as input and generates the required PWM pulses to control the grid tied DC microgrid inverter. These input signals are given to the programmed control system in the DSP controller, which generates the required PWM pulses. Here the DSP generates PWM pulses at a voltage range of 5 volt. The switching voltage range of the IGBT present in the semicron stack is around 12 to 18 volts. The generated 5 volt PWM pulses alone are not sufficient to drive the IGBT switches. For efficient triggering of IGBT switches, the generated PWM switches from DSP are shifted to 15 volt by using a level shifter. Now, the level shifted pulses are ready to give to the semicron stack to avoid grounding issues in the electronic circuit, such as sensor circuits, biasing circuits and level shifter circuits are powered by a common DC source with different voltage levels. Hardware demonstration of the grid integration. Now, before going into the demonstration, let us have a look at the hardware connections. The DC microgrid emulator, that is power amplifier, is connected to the DC input terminal of the IGBT stack. The AC output terminal, that is RYB phases, are connected to the L filter. Each filter box has multiple tapping from 0 to 10 millihenry. For each phase, we have connected 2 such inductor boxes in series to form total inductance for phase of 10 millihenry. The other ends of the inductor is connected to the point of common coupling PCC formed by this MCB. At this MCB connection, bulb loads are connected in parallel path and they act as a load to me. The other side of MCB is connected to the outside of the grid emulator, while the input side of the emulator is connected to the distribution system which is connecting to our campus network. Also notice that after inductors, the wires are passed through the LEM current sensor. For voltage measurement, sensing is done near MCB input and the sensed signal are connected to the LEM voltage sensor board. Before enabling the control loop, the sequence of powering up the test bed is as follows. The first step is to turn on the power amplifier to apply desired DC across the DC side of the IGBT stack. The second step is to turn the grid emulator on the required grid voltage and close the PCC switch. Now the high power circuit has been powered up. Let us power up the DSP and electronic circuits. The developed control system is flashed into the DSP controller through a USB cable. All the electronic circuit that we use here are powered up by turning on a single DC source. Now the low power circuit and high power circuits are powered up. Now it is the time to enable the control loop. The control loop is enabled, and by observing the DSO, there is power flow between DC bus to AC grid. Observing the power amplifier shows the power sign positive. That means it is giving power out. That is, the power is flowing from the DC bus towards the AC grid. Since the DC microgrid is DC bus is stable and has surplus power to cater to the AC grid, the power flow is from the DC bus to the AC grid. Let us move to the islanded mode of operation of DC microgrids. A simple block diagram of the LC filter DC microgrid under islanded mode of operation is shown here. The offsetted outputs of current and voltage sensors are given ADC, that is analog to digital converter pins of DSP launchpad TMS 320 F28379D. The control logic is implemented in floating point DSP. The control logic consists of DC bus voltage control and AC side power control with the help of droop concept. The control logic generates modulation voltages for generating PWM pulses through ePWM pin of the DSP. Now, when we move to islanded mode of operation, let us focus on the control logic in the DSP. The DC bus voltage controller regulates the DC bus voltage at reference value and generates AC power reference values. From AC power reference, active current reference is generated as inner controller requires current reference. The obtained AC current reference is modified by droop controller to maintain stable voltage and frequency at the AC side. Modified current reference are converted to stationary reference frame and then compared with measured currents for obtaining errors. The error is processed through PR controllers for generating required reference modulation voltages. Now, the laboratory prototype of islanded DC microgrid, which represents the laboratory prototype of islanded DC microgrid, which consists of a power amplifier to emulate DC microgrid behavior. A DSP controller simulation converter DC to AC is used as an interface between DC microgrid and AC bus. The power is fed to AC loads through LC filter. Here inductor is to reduce current harmonics and capacitor to damp voltage harmonics. In the same way of grid tied DC microgrid, the control logic is implemented in DSP launchpad. The control logic regulates DC bus voltages and forms voltage for AC loads. Hardware demonstration of islanded mode of operation. In the same test bed, we demonstrated the islanded operation of a DC microgrid. In this test case, the grid is not required. So, the MCB switch is in an open position. The control system of islanded operation is flashed into the DSP controller after powering up the circuit. The AC side of the IGBT stack, is connected to the bulb load. After enabling the control system by observing DSO, there is a power flow between the DC bus and AC loads. The voltage and frequency at the AC load side are stable. By observing the DC microgrid emulator, that is the power amplifier screen, the power sign is positive, which means it is giving power out, that is the power is flowing from the DC bus to the AC load. These are the two major references are being used for preparing the presentation. The first one is on peak energy management using renewable integrated DC microgrid, and then the second one is review and comparison of grid tied inverter controllers in microgrid. I suggest all the student friends to go through those references for better understanding about the fundamentals and detailed simulations. In this lecture, we have learned the operation of a grid emulator and power amplifier. We have experienced how to use a DSP controller in applications of grid integration of renewable energy sources and DC microgrids. The significant benefit of this lecture is that the students can develop their own control system to control an inverter DC microgrid with low cost controller like DSP controllers. Thank you very much for your kind attention. Take care.
Okay, so with this, we end to our day 18 lectures. Now, we will be sharing the PPT related to these lectures and also the links for these videos. So you can see it later whenever you feel so. And moreover, quiz. So tomorrow 19th, then on Friday we will be having 20th lecture. Then on 20th means Friday night we will be sharing mostly Friday night or maybe so mostly Friday night or Saturday morning. We will be sharing you the quiz link on Canvas where you can attempt the quiz as it was previously, and you submit it by Sunday midnight. Now, only thing will remain the conclusion of this FDP. So, whenever sir will present, will inform you and will conclude this entire FDP. So, thank you very much. Thank you.